second session of today. We're going to have 4 talks in this session, and we start with an invited talk by Hinaka Sugiyama on end-to-end encryption in Japan, culture and policy. Please.
Thank you. So thank you very much for having me. I'm Hinako Sugiyama. I'm a human rights lawyer protecting freedom of expression and privacy. And I'm working for the International Justice Clinic at the University of California. So I came here from California Irvine School of Law, where I'm lecturing and supervising law school students. But my opinion and views today I express are totally independent from my clinic. And the fun fact about me is that I spent over 30 years in Japan. So I guess I have a little bit more knowledge about some of you about Japan. So I would like to share with you something about Japan, as title suggests, culture and policy related to encryption. So I think and I hope that you went out and walked around Tokyo a little bit and saw many beautiful, interesting, or something weird. So I don't really have to explain something visible in Japan. So today I'm going to explain, or at least try to explain, something invisible and something related to privacy and encryption. Sounds pretty challenging, and actually it was, but I'll try my best. So are you ready? So, okay, so let me begin with the statistics showing the ratio of use of anonymous names and real names on Twitter. So this obviously shows that in Japan, more people are using Twitter on an anonymous basis, meaning without disclosing who they are in their real lives. And it's a data in 2014, so it's a bit old, but the general impression is that this situation has not been really drastically changed since then. Sorry, it hasn't been really translated, but I just wanted to explain that. Just one more statistics. This shows whether people are comfortable with revealing their real names on social media or not. And so this statistics shows that more people say no and less people say yes in Japan compared to other countries. And combining with these two statistics, perhaps we can say that in Japan, more people are choosing to be anonymous on Twitter to avoid their activities on social media being attributed to their real personalities. So then, some of you might get curious about, so then how Twitter is used or probably used to be used before the ownership change. So for the next couple of minutes, I'd like to show you that hashtag movement, or in other words, online protests, have been happening here in Japan as well, or by using 2 recent examples. So one of the representative hashtag activities in Japan was like 3 years ago. Former Abe administration tried to legislate a law that raises the retirement age for public prosecutors up to 3 years if the cabinet approves so. And the issue was the government did not really provide a sufficient explanation why this is needed, and then which gives the impression that the government tried to increase its power over the public prosecutor's office. And then an anonymous Twitter user created a hashtag saying protesting amendment public prosecutor's office law, and it went really viral. And hashtag was reportedly used about 4 million times, only in 3 days. And Abe administration withdrew this bill. So, and then Twitter Japan chose this hashtag as the second biggest Twitter trend in 2020. So the next representative example is Kutsu movement. There are sometimes really strict dress codes for women at working places in Japan. Something like, as BBC reported in 2019, like prohibition of wearing glasses, or the mandatory wearing of high heels, as this movement was about. So a woman started a movement in 2019 to fight against a rule with the hashtag Kutsu. As you see, tactically, she was using the awake of global Me Too movement. And here, kutsu means shoes in Japanese, and kutsu means pain. So that movement got a lot of media attention, including New York Times in 2020, with the woman's quote. I kept thinking, why can't I talk the same way as boys? And true, gender bias, stereotypes, have been one of the major human rights issues in Japan. The United Nations Committee on the Elimination of Discrimination Against Women, CEDAW, also showed the continuous concern about seeing Japan's persistent patriarchal attitude and deep-rooted stereotypes about the roles and responsibilities of men and women in the family and in society, which is reinforced by the education, media, and also manga, comic books. And the bias and the stereotypes are resulted in the continuous poor performance of Japan in gender equality. So in this index, Japan has repeatedly ranked as the lowest in OECD countries. So among other aspects, women's participation in political and public discussion is also one of the major factors, which is lowering the ranking of Japan. Just give you a sense of it. This is the current Kishida cabinet members. So just circling back to this first statistics, to sum up what I have explained so far. So Japanese people does use Twitter or other online platforms as a civic space for democratic discussion or awareness raising of minority issues, including by women. But the uniqueness lies in the high rate of anonymous use. So the next question, which I'd like to address, is why is that from cultural perspective? Okay, so another statistic shows that these are the top 3 what Japanese people think as Japaneseness and non-Japaneseness. So let me just quickly go through. So, so first one is respect and compassion for others, respect traditional cultures and customs and pass them on to the next generation, or value family or community ties and emphasize harmony and cooperation. And the non-Japaneseness is like finding beauty in things that are rational, functional, and utilitarian. And the second one is following one's own will without being influenced by authority or power, or finding beauty in flashy or gorgeous things. Okay, so for me, there's no surprise for these statistics, meaning, yes, I experienced these discourses are really instilled in education or mass media. So it's a sort of a natural consequences that people characterize Japaneseness and non-Japaneseness in these ways. And the thing is here, so these shared values, which I just explained, turns into one unwritten but pervasive norm. Read the air. I just translated the Japanese idiom into English, but this consisting of 2 sense of obligations. The first one is do what others are doing. So as a result in Japan, once something is reported by a mass media as a new coming trend, people enthusiastically start to follow that trend. And the other one is refrain from doing what others are not doing unless it is strictly necessary. So there might be people who are feeling sick or sad. I mean, that picture, everyone is like seem happy, but there might be people who are feeling sick or sad, but people tended to hide it because if not, it causes sort of self-humiliation that the person lacks an important skills or even not fully qualified as a full member of the society, or it fears of negative judgment by others. So obviously there are pros and cons of this cultural norm. So the pros side, people are really good at acting in conformity and think twice before doing something different from others. So we enjoy very low crime rate, and also people diligently wear masks during the pandemic. But at the same time, so on the con side, people are not very used to make one's own judgment. For example, the government is saying that government position is wearing a mask or not is up to one's decision. But you see a lot of people are just wearing masks. It means people are not really ready to make one's own judgment and seeing how others are behaving in the public places. And also, according to 2018 statistics, taken by the Japanese Cabinet Office. So in response to the questionnaire, like, can you communicate your thoughts clearly to others? And then less than half of Japanese people answered yes, compared to other countries, where 70 to 80% people answered yes. And the second point, which I would like to emphasize today, is hindering people from speaking up. And I believe that this explains the high anonymity rate on Twitter in Japan. And also, people are actually facing real consequences of the mere fact of speaking up, and which even increasing the chilling effect on people. And given that the lifetime employment is still sort of prevalent at a certain degree, so it causes significant effect. So there are tons of examples, but just for the sake of simplicity of my presentation, let me just recycle the same example I used. So some celebrities also supported this online protest under their real names, and such as actors, actresses, singers, musicians, and especially female celebrities. But they were harshly criticized by people on Twitter, by media, or other celebrities, not because of their viewpoint, but because they just spoke up. What I wanted to say here is Japan is a democratic society. It's not an authoritarian country, but rather, so due to its cultural norm, speaking up is still, under real names, are not really easy in Japan. And the person who created this hashtag says Twitter is an important tool for everybody to exercise freedom of expression. So then, yes, I want to conclude here that people need a space to exercise the right to freedom of expression with anonymity, and for that purpose, strong privacy protection and encryption is very important in Japan. And I assume some of you think that this is not really unique to Japan, but it's rather universal when we see whistleblowers are often subject to harassment. So, and if you feel so, I'm glad. And I also expected that reaction, because that's the reason why I keep putting the question mark, like Japanese culture, because my key message here is privacy and encryption are very important in any democratic countries, not only authoritarian countries. Okay, so this is the half of my presentation. So, okay, so I will move on to the encryption policy. So I'd like to start with explaining how the encryption has been used in Japan by taking a look at the most popular messaging app in Japan. It's not WhatsApp, but it's LINE. So in the statistics in 2022, last year, so in response to a question that which messaging apps are you using at least once a week, and the LINE was raised by over 90% of people, Twitter by 50%, Instagram by 50%. And according to LINE, almost 1 million regular users in Japan, and also LINE is a major player in Thailand, Taiwan, and Indonesia, and there are also imminent further expansion into Asia. And just like other messaging app, people can exchange text, images, video, and conduct free VoIP conversations. And the signature function is these stickers. They are really fun. And in addition, LINE is a platform providing various services, include news streaming, online medical service, or like LINE TV, or digital comic distribution. And the LINE is also used for government services, like tax payment, utility payment, or insurance payment. And since 2021, so just as a background, so LINE is 100% owned by Z Holdings Corporation. It's the second biggest Tokyo-based public company in Japan. And that company also owns Yahoo Japan and other internet services. And okay, so Z Holdings is indirectly owned by SoftBank Corp, which is a major investment company and led by Mr. Son Masayoshi, a billionaire entrepreneur and philanthropist in Japan. And LINE was originally owned by Korean parent company, and still, neighbor, a Korean company, owns indirectly half of the financial stake of Z Holdings. Okay, so LINE started to apply letter sealing, which is LINE's end-to-end encryption protocol, around 2015 and in 2016. And end-to-end encryption is applied by default on major services. In 2017, LINE started to publish transparency report, which tells just the same as other companies, the annual aggregated data of their provision of user data in response to the government's request. And at that time, they started to disclose transparency report. Then executive officer who was in charge of privacy and information security in LINE made it crystal clear in a media interview that LINE will never create a backdoor. And at least at that time, it has not been requested by the Japanese government to create a backdoor. And also LINE also publishes encryption report in Japanese and also in English, and also encryption white paper as well. So basically, compared with other messaging apps in the world, I think LINE is doing pretty great. But the thing is, in 2021, investigative journalism revealed that LINE made some of the messaging contents accessible by employees in their Chinese subsidiary. So it created a public backlash from national security grounds, but LINE immediately severed the tie with the Chinese subsidiary. But I see LINE generally enjoy trust from the public. So the next slide, I'm moving on to the encryption regulation policy of the Japanese government. So before October 2020, I could not find any position shown by the Japanese government about encryption. But suddenly, Japan joined a Five Eyes public call, which requests tech companies to create encryption backdoor for anti-terrorism, crimes, child sexual abuse materials, CSAM distribution. And as you may know, Five Eyes is an intelligence alliance comprising Australia, Canada, New Zealand, UK, and the United States. And these countries are parties to a treaty for joint intelligence activities such as bulk data collection, of which abuse Edward Snowden revealed, and the European Court of Human Rights decided that it violated the rights to privacy under the European Convention of Human Rights. And notoriously, around 2017, Five Eyes has been calling for encryption backdoor, and Japan in 2020 signed on this statement. And I researched the discussion at the time, but I could not really find any policy discussion around encryption. And the news article also failed to articulate what is the policy discussion behind this backdoor request. But 2 months before this news, then Defense Minister, Mr. Kono, public showed his position that Japan should strengthen the relationship with Five Eyes in response to China's military expansion. So it seems that this is foreign policy-driven hasty posture without domestic policy discussion, including like implication with privacy and freedom of expression and democracy. And after that, as far as I researched, it's not really crystal clear because available information is really limited on this matter, but it didn't lead to visible legislative policy effort for encryption regulation or mandatory screening of emails or messages. And okay, so one thing also I should very briefly touch upon is the concept of data free flow with trust. The former Prime Minister Abe proposed as DFFT at the Davos meeting a couple of years ago as an overarching framework of cross-border data transfer. And Japan has been trying to take a lead in the international coordination of the expansion of cross-border data transfer, mainly through trade agreements. But this DFFT policy is highly economic-driven policy, so it seems that encryption regulation has not been really on the agenda so far. So in the next slide, I'd like to take a look at the domestic policy discussion over online safety in general. Okay, so since 2018, the ministry in charge of the regulation of ICT sector has been holding an expert panel to discuss and form a policy on the business of online platforms. And overall, the discussion around content moderation was directed toward the self-regulation, like the United States, by platforms. But in 2020, one of the women who were in the reality TV show, Terrace House, so that person committed suicide, reportedly because she had been harassed on Twitter by anonymous users. As you may know, Terrace House follows the lives of 6 strangers, 3 men and 3 women, and they live in the same house while getting to know each other and start to date each other. And in Japan, this program was really influential and popular. So this sad incident sparked the domestic discussion about regulation of online speech platforms to fight against harassment and disinformation. And the good news for us, or at least for me, is the discussions are moving toward the direction of requiring disclosure of the platform's content moderation policy and the status of its implementation, and also resource allocation to content moderation function. It's similar to the Digital Services Act in the EU, and this policy direction does not really include a measure which would compromise encryption, such as mandatory scanning of user-to-user communications like the Earn It Act in the United States, or UK Online Safety Bill, or EU's bill. So, and also one of the reasons why the discussion is going to this direction in Japan is that the constitutional scholars and the lawyers are leading the discussion, and they have a clear position that anonymous speech is important from constitutional perspective, and I really appreciate their strong position. Okay, so don't worry, I'm concluding my presentation. This is the last slide. So again, information is limited, but no visible active effort toward the encryption regulation is not really happening in Japan. But the situation would change. Of course, a foreign policy may create a momentum to push regulation. Also, I might have to say that in past 10 years, the situation of freedom of expression in Japan got worse. As we see, the freedom of press index in Japan has been really steadily declining. So we needed to be cautious about the encryption regulation in Japan, given especially the importance of privacy under Japanese culture, which I explained today. So however, I don't see a robust public debate in Japan about the importance of encryption or regulation. So some security researchers, NGOs, are writing a blog post on this issue, but major media companies are not really following the end-to-end encryption regulation in Japan. So I believe that to vitalize the discussion, reports from overseas media or NGOs would be also one of the drivers to vitalize the domestic discussion. So if any of you are interested in writing about freedom of expression or privacy or encryption in Japan, I'd be very happy to collaborate with you. So just please reach out to me. So thank you very much.
Yeah, thank you very much for the talk. Are there any questions in the audience? Doesn't look like. I don't see the online questions at the moment. I don't know how I can do this, but yeah, maybe then I ask a question. So about the history of the discussion, maybe, of encryption. So when encryption first got, basically accessible to the public in the 90s, we had this backlash in the US and also in Europe, which are maybe now called crypto wars, where governments tried to basically prohibit use of encryption. Was there something similar in Japan?
You mean that time when the encryption?
Yeah, so in the 90s mostly, yeah.
I didn't find, any strong position of the Japanese government. That first one is, as I mentioned, in 2020 when they joined the Five Eyes cause. So rather, it's more like company-driven, I suppose, in Japan. So the company implemented that strong protection of encryption. So that got sort of standardized in Japan. So I think, yeah, that's a brief answer to that question.
Okay, thank you very much. And then let's think, there's a question, I think. Yeah. No. We actually have one question in the audience, yeah.
I was going to ask how you think about the balance of supporting anonymous free speech for people's expression against the balance of protecting anonymous speech from harassment, like the example you mentioned at Terrace House? What's the trade-off in supporting those, and is there a good way to navigate it?
Thank you very much. That's a very, very great question. So to protect or like prevent the online harassment against like free speech there are other tons of measures to implement it for just public education to stop it, or the people who are subject to harassment. So it's also possible that the person can mute that negative remarks about that expression. But on the other hand, regulating the encryption or anonymous speech in general, that is far more bigger harms or damages about the freedom of expression in Japan. So the most like discreet way to address that issue is to think about what sort of like various measures can be taken for the online harassment or other harmful contents. Yeah.
Thanks.
Hi, thank you for the talk. I just have a question about this last point where you say a more robust public debate is needed, but what are the mechanisms for doing that when speaking up is very difficult or frowned upon?
Sorry, could you repeat that?
Yeah, so if you say a more robust public debate is needed about end-to-end encryption, how do you get that going if speaking up is very difficult to do?
Yeah, thank you so much. Possibly people can start to talk about this issue on anonymous basis. Yeah, so that's one way to do it. Yeah, to just start the conversation. Okay. Yeah, and also the company, the LINE Corporation, is really doing very hard to sort of educate people on the ground that their technologies, the encryption technology is pretty important for people. But at the same time, sort of Japanese people's mind is sort of paralyzed a little bit because we are so get used to not to speak up. But the only way I think we can do is start to talk about it. So.
Thank you.
Okay, I think there are no more questions, so then let's ask the speaker again.
Thank you.
Okay, so the next talk is by Kasra, who's going to defend his PhD soon, and he's going to speak about Data Share Network, a decentralized privacy-preserving search engine for investigative journalists.
Thanks.
The stage is yours, yeah.
So, hello, I'm Kasra. Nice to meet you. Today I'm going to present Data Share Network, which is a collaboration with International Consortium of Investigative Journalists, or ICIJ. So, let me tell you about ICIJ. They are, okay, going fast. They are a global network of journalists with over 250 journalists in 100 countries. And they are mostly well known for their work on Panama Papers, which has won them a Pulitzer Award. Now I'm going to open up this a bit more to see how ICIJ operates. This has started when a whistleblower leaked over 11 million documents to this organization, and these documents were already digital and coming in many different formats like images, text, emails. And they had to develop their own tool to process this data using OCR, NLP. And actually, this tool is already available open source on their site. And you can use it yourself too. And more specifically, what this does is that it takes a document, it extracts people, organizations, and locations that are mentioned inside, and journalists' workflow is mainly following links between multiple documents to get what is the big picture. After using this tool to search locally and centrally, journalists came up with the ambition of, can we extend this to do search in a journalist-to-journalist manner without endangering ourselves. And that's when they came to us with this problem. And their needed functionality is first and foremost being able to search. They want to see, they have an investigation topic. They want to see if there is any other journalist in the network who has a relevant document about this investigation. And after finding this person, the second functionality is being able to contact them. And they want to have an anonymous screening talk between them. It's important to note that there is no document retrieval in our system because journalists may not want to share depending on who their collaborator is. And if they want to share at the end, they can use existing tools. Next, we asked them, what are you afraid of? And they told us that they trust each other, and they trust the organization. And they are mainly worried about third-party adversaries like governments, hackers, and corporations. But part of this study, they told us that they are worried about hacking, violence, subpoenas. And these things can coerce or compromise journalists or the organization. So to prevent harm, we had to consider them malicious for protecting both them as becoming a valuable target and harming others in the end. Now let me give you a bit more specific on privacy requirement. We need to make sure that when doing a query, the querier can hide her identity and the content of the query, which is her investigation. And on the other side, document owners want to protect the content of documents. I'm going a bit fast here. Sorry. And when in the contact phase, journalists want to hide both the content and existence of any conversation. As for operational constraint, we need to support up to 1,000 journalists, and each journalist has gathered around 1,000 documents on their personal computer over the time. Before trying to build a system, we asked ICIJ about their IT infrastructure. And they told us that they can only deploy servers on clouds like Google Cloud, Amazon Cloud, and they do not have their own big IT servers. And this means that any approach that relies on decentralized trust or any trust is infeasible. And beyond that, they told us that these journalists are not willing to upload their documents for processing to clouds, so trusted third parties is out of the question too. Next part, as you can see in this image, these journalists are living all across the globe. They work at different time zones and sleep at different time zones. So some of them are never online at the same time. So we need to deal with asynchrony. This means that any approach that relies on multi-round SMC or MPC protocol is out of question too. And finally, some of the countries that you can see in here, especially in the middle, do not have fast, reliable, and unlimited internet connection. So communication is a scarce resource for us and is more important than computation. So approaches like garbled circuit and fully homomorphic encryption is out of question too. To wrap this up, we can only have a single malicious server that is only trusted for availability. Now let's build our document search. The privacy recap is this search needs to protect the query, documents, and the result of matching. And the search can be simplified as are queried keywords inside a document or not. And to do this, we design a new cryptographic primitive called multi-set private set intersection, which is an extension of a protocol that you are already familiar with called PSI, where Bob has a set of input elements and a secret key. Alice has a set of keywords too, and first Bob computes a PRF with his key or his element and send them as tags to Alice. And next, Alice and Bob perform an oblivious PRF together, where Alice can compute PRFs with Bob's key on her keywords. And by comparing these two sets of tags together, Alice can compute the intersection. Now, this is great when you have one document. we have thousands. It's becoming a bit more troublesome. And we have thousands of journalists. Now this is prohibitive. And what we do next is that we extend this protocol to remove the 1,000 factor that we get from having many documents. And to do that, we allow Bob to have many documents and many sets at the same time. And to do so, we add a diversifying step to how we process our tags. That after computing the PRF, we hash them with a document identifier. We keep the OPRF part intact, and in the end, Alice can locally compute the same diversifying hash and compute the intersection for different documents. Moreover, we can do this in a setup online phase that the expensive part of computing tags in the beginning and sending them to journalists can happen only once, and it's reusable to reduce the cost. And as you can see here, this drastically reduces the cost and make it practical for our deployment. Next, there is a problem in here that we are considering a new, stronger privacy setting. We have confidential documents, and we give search access to the adversary. There are some fundamental limits in here, like, again, double-clicking, that can we hide the existence of Snowden leaks from like this adversary in here? And as you see, no. This, as a disclaimer, is an out-of-context code. But I don't really mind me telling you that you cannot hide these Snowden leaks. But to show you how this happens is that many of these investigations have a specific terminology in them. Like there is a word, X key score, that only happens in the context of Snowden leaks. And if adversary searches a keyword like this and find a match, then it's clear that the only way that this can happen is that these documents are leaked. While I'm telling you that some protection is not possible at all, not all is lost, and there is still some level of protection that we can provide, and this mainly goes into preventing extraction of keys from documents. And the most practical way to do this is by rate limiting the number of queries and the amount of information in each query. And to do this, we use single-use blind tokens that have the additional benefit of allowing us to do authentication and make sure that only authorized ICIJ journalists can perform a search. Now that we are done with the document search, let's start with our contact solution. And as a recap, this contact needs to hide both the conversation and its existence. So first, we try to use existing systems, but none of them fully satisfied our requirement. For example, if you want to use Signal or Telegram, you need to start with telling them what is your telephone number, and you cannot hide this kind of metadata. And when you go to solutions like Talks, which is an anonymous messaging relying on Tor hidden services, you have the requirement that both user needs to be online. So they do not support asynchrony. So in the end, we had to build our own anonymous messaging system. And to do so, we use Diffie-Hellman key exchange between an ephemeral key of a querier and a document owner key to compute a random rendezvous mailbox to exchange messages. And whenever we want to send a message, we add cover messages and shape outgoing traffic based on a Poisson distribution. On the other hand, when retrieving messages, we use private information retrieval to hide the ID of which messages are getting downloaded. And in the end, we integrate Tor into our system to make sure that none of these steps leak network artifacts to adversary which can be used against these journalists. Now that we designed the system, we perform a user study to help us configure the trade-offs that we have. Okay. And we mainly care about 3 types of trade-off: functionality, querier privacy, and document owner privacy. And to do this, we show 3 systems to journalists, and I'm only going to talk about 2 of them here. The first one is the MSPSI protocol that we built earlier, and the second one is an off-the-shelf search engine called Lucene, which is very similar to what you get when interacting with Google. This gives you way less privacy, but better functionality. And in here, I'm showing you the response for 2 of these search engines. I know that you cannot see details, but in this slide, it's not really important. It's just the size that matters. That you can already, without details, see that the size and expressiveness in Lucene is way more than what we can provide. And next, we design our user interviews. Fortunately for us, we are working with journalists. So we ask them, can you build a fake investigation for us? And we ask them to only use publicly available leaked documents to do this. And we start interviews by telling the user that pretend you are Jamie. Jamie is a journalist working on tax evasion by Big Corp. Then we tell Jamie that you have some tasks to perform. For example, you heard rumors that Verizon is doing tax evasion. Can you find a journalist who has relevant document for this investigation? And finally, this is a peer-to-peer system, but we are interviewing 1 journalist at a time. To be able to handle this, we simulate the rest of the network and tell Jamie that, hey, there are 10 other guys in the network. 2 of them are taken hostage by bad guys. Now, as you have seen before, seeing the functionality of a system is straightforward, but how can we show the privacy to them? We rely on 2 approaches. First, we give them interactive hints that when they do their first PSI query, we show them that if you want to query for term tax, you need to send a random blob. And we ask them to write this random blob down and confirm that this is what's sent over the network. Then we go to Lucene and tell them that, oh, if you want to search Trump, you need to type Trump in, and this is what everyone in the network sees. And we actually show them that the queries that are arriving, that, for example, here for PSI, these are just random blobs that they cannot make any sense out of it. The next part is we flip the table, and we give them an adversarial view. We build an over-the-shoulder view where we translate the leakage to what other journalists can learn about them. Like, we had 10 other journalists in the network, like Charlie, and we tell them what Charlie knows about your documents. And again, in here, you may not see the detail well, and the only part that matters is that the size of information that is available in Lucene, you can already see is more than what happens in MSPSI. And we are very explicit with journalists that this view that you get here is only available and possible during this simulation. Our preliminary result is that despite the lower functionality of MSPSI, journalists prefer it because of its privacy. While doing the user study, we went ahead and developed the system. And now I'm going to share some of the lessons that we learned during this process. Okay. So first, we had 4 major aspects in our deployment that we needed to deal with: UI, UX, authentication, document search, and messaging. And the first 2 are not that visible into the academic setting of writing the system. And our first lesson started when we tried to build and integrate our authentication system that you need to deal with legacy code. So in our paper, we used anonymous credential light and Abbott's blind signature for these single-use blind tokens. They are very well-known cryptographic primitive. I think we even have authors here. And theoretically, it's done. Good approach, secure approach, everything perfect. And implementing it is very straightforward, too. The problem comes up with the fact that these journalists are very wise, and they have multi-factor authentication. And one extra part of this is that they have their own internal OAuth system, which is something built in-house using Ruby on Rails with a lot of interesting things inside that make this integration very memorable. The next lesson is that you need to prepare for having a cold start. We need to design the system for its stress test of like having 1,000 users, but we are going to just start with tens of users and reach to 300 active journalists in a few years. This is a very different operational point. And for some aspects like privacy, which loves company, parameters that are secure and private for 1,000 users may not be safe for just having 10. And okay. The final lesson is don't think complicated. When we designed the messaging system, we were arguing internally that we need to use a PIR. Should we use computational PIR and add homomorphic encryption? Or we should go differential private way and do epsilon PIR. In the end, what we deployed is, hell no, we are not going any of them. We are going to download all messages. This is fast, efficient, and private for our setting when we are in our beginning phase. Then after deploying this and system getting more use, we have time to slowly build on top of this and build algorithms that allow us to scale at the later stages. Now I'm going to tell you why I think DataShare has succeeded and we are getting deployed. And the funny thing is that most of these reasons are not visible at all during this talk to this point. First, we are working with real journalists. They wanted to have this tool, and they were pushing to make it as usable for them as possible. And to do this, they were involved in all stages of this process. They were there during requirement gathering, design, user study, and finally in the development and deployment. And next part is that we had amazing dedicated engineering team, both in our lab and with journalists. And they were the ones who built the system. And finally, there is a lot of time and resources spent on making this system. We were many people. We worked for the better half of the decade. The paper came 2 years ago, and we just reached to our first beta test in like 2 weeks ago, which is a very long span of time for spending on one academic paper. And that's it. If you want to have a usable, deployable system, researchers are not enough. You need to have users and engineers to build the system too. And thank you for listening to me. As Gregor mentioned earlier, I'm finishing my thesis soon, and I'm on the job market too. So if you have anything interesting you want to talk or email, I would be super happy to do that. Thanks.
Yeah, thank you very much. Any questions? This time I also see the online questions, but there are no. Yeah, then I think in the interest of time, since we're a bit over already, let's thank the speaker again. Okay, so our next talk is by Trisha Datta on using ZK proofs to fight disinformation. Please.
Hi. Can everyone hear me? Yeah? Great. So hi, my name is Trisha Datta, and today I'm going to be presenting joint work with Dan Bonnet on using zero-knowledge proofs to fight disinformation. Now, I'm sure over the past few years, we've all heard a lot about misinformation and disinformation. My talk today is going to focus specifically on photographic misinformation and disinformation. And in particular, I'm going to be talking about this issue of image provenance verification. Now, when I say image provenance verification, that's basically just a fancy way of saying that we'd like to be able to verify when and where images have been taken. And we think that this kind of verification is particularly important in the realm of journalism and news media. So imagine you're looking at a news article on your phone or on a browser on your computer. You'd like to be sure that the photos that you're seeing in the article were actually taken when and where the article claims they were taken. And to give you an idea of why we think some kind of formal verification might be useful, on the next slide, I'm going to give you some examples of where this verification would have been very useful. So one example of a recent event where there's been a lot of photographic misinformation is the Russian invasion of Ukraine. And here we've seen a couple different flavors of disinformation. So one is where you'll see a picture that is supposedly of Ukraine, but is actually of somewhere completely different, like Syria. And so in that case, you'd like to have been able to verify where the photo had actually been taken. You also see instances where the pictures you're seeing are actually of Ukraine, but they were taken years before the invasion. And so in those instances, you'd like to have been able to verify when the photos had actually been taken. In addition to kind of just sowing confusion and being generally incorrect, misinformation can also actively cause harm. So with the recent devastating earthquake in Turkey and Syria, misinformation was actually actively impeding relief efforts because it was preventing humanitarian organizations from knowing how to best allocate their limited resources. And this last example I actually think is the most compelling in terms of what I'm going to talk about today. So basically what happened is a BBC show showed footage of what was supposedly the Russian invasion of Ukraine, but it was actually just footage of a Russian military parade rehearsal. And the reason why I think that this is particularly compelling and motivating is that the BBC is a reputable news organization. Presumably, they have teams of human fact checkers and verifiers whose job is to make sure that this kind of thing doesn't happen. And so the fact that it still happened means that there's definitely room for improvement in current image provenance verification processes. And of course, there are policy responses that could take place. But hopefully what this talk will convince you of is that there are also technical solutions that can be developed, and that's where we as computer scientists and cryptographers can come in. So one example of a technical solution that's been proposed is the C2PA, which is a content provenance standard, and the C2PA has been developed in conjunction by a bunch of different organizations, including tech organizations like Twitter and Microsoft, as well as news media organizations like the BBC. And essentially what the C2PA proposes is that every digital camera be equipped with an embedded certified signing key, and actually as of August of last year, Sony is producing a camera with this technology. And so every time one of these cameras takes a photo, the location and timestamp of the photo would get recorded, and then all of that information would be signed by the signing key. And then if you see this photo in your browser in a news article, you would be able to, the browser would be able to verify the metadata of this photo by simply verifying the camera signature. Sorry. So for the purposes of this talk, we're going to assume that you can't extract the embedding key from the camera, and I'm going to focus on a different area for improvement that we see in the C2PA. But if you're curious to learn a little bit more about potential risks and associated with using this standard, you can refer to this talk. So the issue that I'm going to talk about today with regards to the CPA is how to handle post-processing. Now, post-processing basically refers to any edits made to the photo between when it is taken and when it is published in a news article online. And usually at minimum, photos are downsized from their original size so that users don't have to download these gigantic photo files. And just to give you an idea of size, that Sony camera that I mentioned on the previous slide, the pictures that it takes are about 30 megapixels, which would be about 90 megabytes, and they might be resized to something like 8 megabytes, and that's just a number we got from looking at articles on the New York Times. In addition to downsizing, there are several other edits that may occur to a photo before it is actually published. The Associated Press actually has a list online of what they call allowable edits. So these are things that basically do not change the fundamental character of the photo, and they include edits like converting to grayscale and cropping and other minor coloration edits. And the reason why post-processing kind of puts a little bit of a wrinkle in the scheme that I described on the previous slide is that in order to verify a signature, you need access to the thing that was signed. But if the browser is only viewing this post-processed photo, then it obviously has no way of verifying the camera signature on the original photo. And so the C2PA does have a proposed mechanism for dealing with this. Essentially, it involves getting a trusted third party to sign attestations of which edits have taken place. But having a trusted third party is not really ideal. It introduces this point of failure. And so it'd be nice if we could somehow have proof of which edits have taken place without this trusted third party. And hopefully this should be no surprise given the title of this talk, but what we are proposing instead of this trusted third party is the use of ZK snarks. And I'll just give a quick little refresher on ZK snarks. So you can think of them as efficiently verifiable statements about a secret witness. So basically how this works is we have a prover and a verifier, and they both have access to some kind of public information, which we call the public statement. And the prover has access to a secret witness that the verifier does not have access to. And essentially what's going to happen is the prover tells the verifier, hey, verifier, I claim something is true about my secret witness, and I'm going to give you this proof pi to prove it. And the verifier says, thank you, I'm going to take this proof pi, and I will check it. And if the verifier's check passes, then they will be convinced that the prover's claim is true. And if it fails, then they will not be convinced that the prover's claim is true. And ZK snarks have 5 very important properties. So the first is that they are complete, and this means that if the prover's claim is true, then the verifier's check will pass with very high probability. They are also sound, which means that if the prover's claim is false, then the verifier's check will pass with very low probability. They are non-interactive, which means that the prover and the verifier aren't sending a bunch of messages back and forth. The prover is just sending this one message pi, and any verifier can check it. They are also zero knowledge, which means that the only thing that the verifier is learning about the secret witness is whatever is implied by the claim. And they are also succinct, which means that the verifier's check can be performed efficiently. Okay, so how does this apply to our photo situation? So basically, instead of a prover and a verifier, we can think about this in terms of the news organization and the web browser. And what the news organization is basically trying to convince the web browser of is that all of the photos in the article, which again are post-processed photos, so it's trying to convince the verifier that all post-processed photos were taken when and where the article claims they were taken. So in terms of the public information that both the browser and the news organization have access to, they both have access to these edited or post-processed photos, as well as a set of operations, which is basically going to be a subset of that list of allowable operations from the Associated Press. And these are the operations that have been applied to the original photo to get this post-processed public photo. The secret witness is going to be the original photo, as well as the camera signature on the original photo. And then the news organization has to convince the web browser of 3 things. First, that they have an original photo with a valid signature. Second, that if you apply this set of operations ops to the original photo, you will get the public edited photo. And then third, that the metadata of the edited photo is equal to the metadata of the original photo. And the cool thing here is that this system that I've just described is using all 5 of those properties of ZK snarks that I just discussed. So the completeness and soundness means that the verifier does not need to trust the prover, and that gets rid of that trusted third-party constraint in the C2PA. The non-interactivity is important because if these proofs were interactive, that would mean that the news organization would have to exchange messages with every browser that viewed the article, which is obviously not ideal and wouldn't make this a feasible system. The zero knowledge property is useful if we're applying an operation to the original photo, such as cropping, where maybe we don't want the web browser to know what was cropped out of the photo. And the succinctness is useful because that means that the check that the web browser performs on the proof is efficient, which means that we can reasonably expect these browsers to actually perform these checks. Okay, so in 2016, Neve and Schromer published a paper called Photo Proof, which was basically, they showed that you could create zero-knowledge proofs for photo edits. And this was really cool because it was a great proof of concept. But unfortunately, it took them a few minutes to create these proofs for images of about 128 by 128 pixels. And if you'll recall, that Sony camera that I mentioned at the beginning, it produces pictures of about 30 megapixels, which is obviously several orders of magnitude larger than 128 by 128. So while this was really cool, the technology wasn't quite there yet to make these proofs for realistically sized images in a reasonable amount of time. The great news is that since then, there's been an explosion in ZK Snark technology. These are just some of the many tools available to developers now. And basically what this means is that we now are able to create these kinds of proofs for realistically sized images in a reasonable amount of time. So we created editing proof generation programs for 3 different types of edits, resizing, cropping, and grayscale, which are all from the Associated Press list of allowable edits. And we performed experiments for images of about 30 megapixels, which is, again, the size of pictures produced by that Sony camera. And we wrote these programs using SIRCOM, which is one of the tools I listed on the previous slide, which is basically a general-purpose zero-knowledge programming language. And when we talk about timing for these proofs, we want to talk about 2 different elements of timing. First is how long it takes to generate the proof, and second is how long it takes to verify the proof. And the kind of main difference between those 2 elements is that we only have to generate these proofs once per image, and that is performed by the news organization, whereas every browser that accesses news articles will have to verify these proofs. So while proof generation needs to be fast, proof verification needs to be very fast. And what we see is that proof generation, which for SIRCOM consists of generating the proof as well as also doing some kind of witness generation, that takes a few minutes, which again is reasonable because this only has to be done once per image. And proof verification is very fast, again, due to the succinctness of ZK snarks, and it only takes about 2 milliseconds. Okay, so if we go back to the 3 things that the news organization needs to prove to the web browser, I've talked about the second step, which is proving that the post-process photo is the results of applying certain edits to an original photo. The third bullet isn't as interesting. I haven't talked about this first bullet, which is proving that we have a valid signature on the original photo. And unfortunately, this turns out to be the bottleneck. So what we want to do is we want to prove that we have a hash of the original photo and then that we have a signature on this hash. And ideally, we would do this for a standard hash like SHA-256. Unfortunately, it takes a lot of time to produce this kind of proof for a 30 megapixel image using SHA-256. And the kind of intuition as to why is that it takes a long time to generate proofs for nonlinear constraints, and SHA-256 has a lot of nonlinear operations. Now, there are hash functions that are designed specifically to be snark-friendly. One of them is Poseidon. And so you might think that we could just use Poseidon for our 30 megapixel image. But this also turns out to be too slow and not practically feasible. And so what we end up doing is we take a lattice hash of our original image, and then we take a Poseidon hash of the lattice hash. And this ends up working. And we think that this construction is kind of independently interesting as a way to hash really large things within snarks. Okay, so I'm just going to go into a little bit more detail about this hash construction. So essentially, we're applying a standard lattice hash to the original image, and how this works is we create A, which is a random matrix over a finite field, and then we represent the original photo as a low norm vector in this field. So this is the thing that is being hashed. And then we multiply these 2 things together, and this gives us our lattice hash. And this is still pretty large, so what we do is we just run this through Poseidon, and that gives us our eventual hash. Now, the intuition as to why this is faster than something like SHA-256 is this matrix multiplication in the beginning is basically just a bunch of linear constraints, and it's much faster for us to generate a proof for linear constraints than nonlinear constraints. The kind of trade-off that we have in doing this is that this hash function is only collision resistant, assuming SIS. And so in addition to proving that we know this pre-image that hashes to this final hash, we also have to prove that this pre-image is low norm. So how do we prove something is low norm? There's a pretty cute little trick that we do. Essentially proving that something is low norm is proving that all the elements are between 0 and this limit R. And so I'll have this picture on the side illustrating what I'm talking about. But so we have our R, we have our X, which we're trying to prove is low norm. And then we create another vector Y, which is all of the values from 0 to R minus 1. And then we create a third vector Z, which is the sorted concatenation of X and Y. So first we concatenate X and Y, and then we sort it. And now that we have Z, we have to prove two things. One is that Z is a permutation of the values in X and Y. And two, that the differences between consecutive values in Z are 0 and 1. And intuitively, what this proves is that the values of X are contained in Y. Okay, so this is a graph showing our timing results for generating a proof with just the Poseidon hash versus generating a proof with the Poseidon plus lattice hash construction. And you'll see that for smaller image sizes, it is more efficient to just use the Poseidon hash. But for more realistic image sizes, specifically those last two dots, that's that magic 30 megapixels number, you'll see that the Poseidon plus lattice hash construction is much faster. And actually, we couldn't even get the Poseidon hash proof to actually finish. We ran out of memory. So that's a projected point. So in conclusion, I think kind of the big picture takeaway from this talk is that there's been a lot of improvement in ZK Snark technology, and this has mainly been driven by applications for the blockchain, but there are also a lot of other really cool applications that we can use ZK Snarks for, and we've seen a bunch of others in other talks in this conference. In particular, in this talk, we show that we can create photo editing proofs for realistically sized photos in a reasonable amount of time, and a kind of obvious application of this is for image authenticity in the C2PA. And one interesting open problem is in this talk, I've only really talked about photos, but there is also misinformation in terms of videos. And so one thing to think about is how would we go about creating these kinds of proofs for videos? And that's it. Thank you.
Yeah, thank you very much. I see there are a lot of questions. So please, on the right-hand side, go ahead.
The first thing that came to my mind was that C2PA is going to be the same problem of SGX problem with having to rotate your keys and so on. I already smell that, and some maybe talks next year about that. Mm-hmm. So your concern with SHA-256 was it was linear. Have you considered using parallelizable function like, I don't know, Kangaroo 12?
We did not consider that, but that would be definitely another option to look into, yeah.
Because Kangaroo 12 like hash blocks by blocks of 8,000 bytes, and so you can literally parallelize that over 256 core or whatever parallelization you can. So that's a very nice trick that you could have maybe considered.
Yeah, no, I think that sounds very interesting, and I think there's obviously much more to be done, and making this even faster is obviously a good thing.
Thank you.
Thanks.
Yeah, I have a question about the threat model. So I'm wondering if you try to keep the identity of the camera private or not, and if you do, how do you protect against physical compromise of a single camera that can then be used to provide forgeries with the guarantees of never being caught?
Sorry, I missed the word you said. Trying to keep what private in the camera?
The identity of the camera, the public key of the camera. Is it private or not? And if it is, how to protect against physical compromise of one camera?
Yeah, I think in our threat model, it's not private. Yeah.
Thanks.
So suppose there is an edit picture and a proof. And now I want to re-edit this picture. So how do I generate the proof? Can I use the existing proof, or I generate the proof from the beginning? I think if I use the former, the verifier needs to check two proofs, and the verifying time will be doubled. And I think if I use the latter, the proof generation time will be larger. So how do I choose?
Yeah, so actually I think the proofs are designed that you can kind of like stack them on top of one of another. So I think it would actually be the second thing that you said, where the proof generation time might double. But again, because it's only happening once per image, it's not really a huge concern.
Okay, so I get it.
Yeah.
Okay.
Thank you very much for the talk. So I was curious, have you given any thought to handling like semantic preserving edits? So you can imagine a case where because the original image is in the witness, I give you a legitimate edit, but the edit modifies the semantics of the picture to imply something different than the original photo intends. And so how would you handle a case like that?
Yeah, so the thing about these proofs is that the operations are public, and so if you're making an edit that changes the semantics of the photo, then you would be able to see that that is the edit that has been made. And so like you as the browser as a verifier could flag that and be like, well, this is not changing, this is changing the fundamental nature of the photo.
Okay, so presuming the original user has the original picture available to them.
Well, no, because the edits that are made to the photo are part of the public statement. So if you make some kind of, I guess, are you saying I guess you're talking about the case where it seems like an innocent edit, but it's changing the, I see.
Yeah, I'll follow up afterwards.
Yeah.
Yeah, thank you.
Yeah.
So unfortunately, we don't have time anymore, so we need to take these questions offline and go to the next talk. Thank you very much. So the next talk is by Joshua Barron, and he's going to speak about, I was told there would be a blockchain 5 years of real-world crypto at DARPA.
Hi, everyone. I'm Josh. I'm a program manager at DARPA. So DARPA is a funding agency. The D in DARPA stands for Defense. We're the Department of Defense's kind of high-risk, high-reward research agency. We've been involved in cryptographic research for the last 10 years. I've had the privilege of being at DARPA for a bit over 5 years. And so really, this talk is going to be a little different. It's going to be incredibly scattered. So literally every slide is going to be at least one new idea and probably more than one. So it'll be a journey that we will all be on together. And I put the word blockchain in there because I thought I would be funny, but the truth is that I have done nothing blockchain over the last 5 years, with one exception. Okay, cool. I'm figuring this out. With one exception, we did fund some work at a Trail of Bits, looking at the underlying thinking through centralities and distributed ledger technologies, because it turns out when you build a distributed system, there are any number of ways in which it's not so distributed. And so there's impacts in that, and I encourage you to read that report because it's pretty fun and interesting. But again, that is the entirety of blockchain we will be talking about today. All right, so in the beginning, there's a program called Proceed, which was doing fully homomorphic encryption a very long time ago. By a very long time, I mean like 10 years ago. And we've been doing at DARPA a number of programs. And by doing, let me just step back. Again, we're a funding agency, so I want to be really clear. Everything I'm going to talk about, I just paid for, which is to say I took the government's money and paid for it. So I did nothing. I'm just presenting other people's ideas and pretending that I'm cool. So that's literally like what we're going to be doing here. Okay. So there are a bunch of programs. I'm not going to go over all of them in the interest of time. But today, we'll see. I'm going to try to hit very briefly 4 different programs, each of which, again, I'm really not going to focus on kind of how we did it, and I'm going to more focus on what we did. Okay, so there's probably going to be, well, anyhow, let's get going. So Brandeis is a program that actually ended like 18 months ago, 2 years ago, a while, but it still takes time to actually release code. And so one thing that just came out last August was a program, a open source Android app called Coffee Break. And if it's you and up to 10 friends want to find a place for coffee, which is to say you want to find a noisy, and noisy is important here because if it's not noisy, you can kind of geolocate everyone else, a noisy median point. You can do a garbled circuit MPC. So in other words, it is comms channel agnostic. We use RabbitMQ, but it doesn't really matter. So you're actually doing full multi-party computation on Android phones. It takes a couple of minutes in the 10-party case, and you can find a place to meet up. What's really fun is that if you think of what Proceed was, which was FHE, it was this whole, like, everything goes up to the cloud. This is the total opposite. This is doing full up, straight, garbled circuit MPC, 10 parties, where all the computation is actually happening on phones. There's no offloaded computation into the cloud. So if you think that's fun, again, the software is up on GitHub, and yeah. All right, moving on. We're going to talk a little bit about a program that started 3-ish years ago, maybe a little less, called Everything at DARPA has to have a funny name. That's like how we talk. So it had to be CIV, which stands for something, and I actually had to look up what it stood for, even though I created it like 3 years ago. And so it stands for that thing, but we call it CIV. And so really it's this idea of creating mathematically verifiable public statements derived from hidden yet sensitive information in order to publicly yet securely communicate about DoD capabilities. Really, we're not going to talk about the DoD stuff right now because it's kind of less of interest to this room, and we're going to talk much more about, candidly, what we've been mainly focusing on, which is like everything else that we've been trying to do. And so it would not surprise you to know that there is a lot of research happening right now in the zero knowledge space having to do with cryptocurrencies. And a lot of that are therefore kind of statements about paying for things. I'm not so much interested in zero knowledge about paying for things. I'm interested in zero knowledge about really any number of other things. And so the way we actually structured our program was there's the kind of standard thing of how do we build really fast zero knowledge, but then the other is how do I take like general statements and then actually turn them into intermediate representations that are friendly for zero knowledge proofs and then do zero knowledge proofs. The other thing that's kind of a major differentiator for what we're doing versus others, we're not as focused in the non-interactivity, though we do non-interactive work, and we're definitely not as focused on the succinctness. And the reason we're less focused on succinctness is because in many cases, as we'll see, our proof statements are massive, like massive. And so anything that's super linear, we just take a massive hit and everything dies. And we're going to get into kind of what that means. Okay. We are funding a ton of people, US focused, but we're definitely funding folks that are not only in the United States. People often think that DARPA only funds people in the US, and that's 100% not true. We love working with foreign companies and people, and yeah, we're very friendly over here at DARPA. All right, next slide. I don't know why I just said next when I can click through next. Force a habit. The kind of three types of, actually, let me just go back to just real quick. Here's the thing to understand. On the right, I think of it as like the car. It's building the really fast car. It can do a lot of things, but like what can it do? Well, it can do whatever we build statements for. Right? So this is kind of awesome because I can build things that like make really fast ZK proofs, but really what I care about honestly is how do I make cool ZK statements, right? And then efficient ZK statements, okay? So that's what we did. We funded like 6 different teams. I can count, yep, 6. To do different things along 3 different kind of areas. One is in statements about software, one statements about computation, and then one's socio-technical. So software will literally be proofs of like vulnerability and security and stuff like that and exploitability. Computation is the kind of more standard zero knowledge, verifiable computation type stuff. And then socio-technical, we will see. So why do we need giant zero knowledge statements? One of the things that we were kind of interested in, just stepping back, was the original SNARKs paper was that, SNARKs for C, right? And so when I saw that initially, I was like, well, that's really interesting. We're taking the C code and compiling it down into a thing that we can do ZK proofs on. Can we do ZK proofs of like exploitability of C code, right? And the answer at the time was like kind of sort of not really. And the reason is because how you compile down matters, and often if you're just compiling for how the C code works, you're missing critical details of the underlying system where the vulnerabilities live, right? So like as a straw person, like if you just have str copy in the code and your proof is there exists a bad piece of code in there, like that's rather straightforward. But if you want to talk about like memory corruption, or if you want to even get down into the underlying ISA, right, and actually say like something is happening in the like as when you compile down to assembly, these are very, very different things. And as a result, your statements get massive because your underlying representation has to actually cover, right, all of that abstraction, right? It's like, well, not, yeah. Okay, cool. So we're actually doing it in 2 different ways. We actually took the MSP430 microcontroller. This is Trilobit's work, and they actually took a capture the flag, and they did zero knowledge proofs of exploitability for all those capture the flags. Their next trick is going to do an actual reduced ISA version of x86, and I'll talk about more of that later. And again, actually, they're not like MSP430 is like this tiny thing, so like it doesn't blow up too much. But then for our next, that's what Trilobits is doing. Galois is more looked at kind of C code and program traces. And so I think, yeah, so this is going to be at Usenix. The previous work that I just mentioned is at Popets on the MSP430. The Tiny86 stuff isn't out yet. This stuff I'm about to talk about is at Usenix, and it's actually a zero knowledge proof of Heartbleed. So I could take the OpenSSL code and show that there was a buffer, there was a memory corruption issue, right? Now, just to be clear, right, this is also the subtlety. The statement about the exploit matters, right? So like as an example, it's extremely difficult to capture like row hammer, because then to do that I have to actually like, you know, but if I want to talk about just like there exists memory corruption in like Heartbleed versus like this line of code has a vulnerability, which would obviously be a much smaller statement, right? So look at the multiplication gates, that's in millions, so that would be 17 billion gates, okay? That is large. I think where are we in Zcash right now? It's in the tens of millions is the current size of that circuit. Yeah, ish, cool. Luckily, we have really fast zero knowledge. So our Galois team, based off of, this is, they published the original work in crypto, but this is a faster version of it. We are doing zero knowledge proofs on AES computations that are only 100x slower than the software implementations of AES, not hardware, that would be really cool, but software. So we're at 4.5 nanoseconds per AND gate. For that tiny 86 stuff, we're at 3.0 nanoseconds per AND gate, which actually is about a 15.25 kilohertz zero knowledge processor for tiny 86, right? So that's not great, but that's getting kind of interesting. And that's like sick fast for what it's worth. Suppose you didn't want to do that like crazy standoffish stuff, but you wanted to do something that literally just lived in the browser. One of our teams, Lajero, actually has work where you can actually do full up zero knowledge proofs and verification in the browser via like WASM code. It's extremely, again, even there we're talking at microseconds per gate. So it's not like, it's slower, but it's not slow. In fact, that will be, please watch out for that work as it gets published. It's really interesting, and you can do a lot of really interesting things in that work. Okay, next. I said next again. This time is going to be fun. Break, totally different thing. We also care about society. One of the really exciting things, cool, we can get into the really nitty gritty on, like no kidding, like really, really hardcore stuff in terms of how we think about computer systems, right? And how do we create these abstract models of computer systems? But also, how do we do zero knowledge things that are relevant for like policy? Right? And so one of the things I'm really proud of is that in the recent computer science symposium on computer science and law, I think it was like a quarter to a third of all the talks were funded by us. And again, that's just really awesome, and that's a real credit to the team at BU and MIT that we're funding. One paper I wanted to highlight is the Balsa-Nissenbaum-Park paper. That's about how cryptographic, and it was really hinted at a couple of times over the last couple of days, the way that we cryptographers talk about trust is very, very different than how like normals talk about trust. It would behoove us to understand what they want and not try to get them to do what we want, right? Just, anyhow, that's the thing to look at. Also, we have papers in law journals, which just tickles me and is really, really cool. And who knows, that might, I think that could be kind of fun. All right, next. All right, so force a habit. Last thing on the zero knowledge side, and then we're going to do something completely different. I'm assuming I can go 5 minutes past the hour, and if I can't, this is going to get sporting. This is an interesting proof on, it turns out in Estonia, to get a subsidy, your car has to like spend a substantial, like a very specific amount of time like on the Estonian roadways, right? Now, I don't want to have to tell you everywhere where I drove for like the obvious reasons, right? But can I do a zero knowledge proof based off of some like basic Raspberry Pi thing, hardware like dongle, that actually shows that I've done that without revealing anything, right? So in other words, I have done the requisite driving, but I'm not going to tell you actually where I drove. So they actually already built this, and it's sitting up. Again, one of the cool parts, one of the things I love about DARPA was that, and the way that we do this work is that this was done by Cybernetica out of Estonia, but the ZK technology was actually done by Galois. And so they're actually like working together on this. This is not published, this is like super, super new stuff. Like this is a picture from like a week or two ago. If you have any questions, Dan Bogdanoff at Cybernetica, or just talk to me. I think this has a lot of implications just generally for how we think about following people and not trying to like actually reveal too much about like things that might have to do with like geolocation specific statements. There are also like a flip side of that, obviously, but we'll talk about that another time. Now for something completely different. We're going to talk about anonymous communication, okay? Tor is great. Tor is incredibly distributed. Tor is so distributed it has to announce where it lives. Because it announces where it lives, it's targetable. So the question is, can I do less than Tor and only do messaging? And so maybe if I do that and then I build a distributed system, I'm not so targetable. And so the kind of two things I have to do are MPC-based message passing and hidden communications. That's a very, very high level, and I can talk a lot more about it, but I'm not going to because of time. So basically, there are three parts. We have 2 teams doing cryptography, stealth, and SRI. We have 4 teams doing hidden communications. That's Georgetown, NRL, Tor, STR, SRI, Princeton, Chicago, and Galois. And then some folks doing integration. We work very heavily. We do work with DoD, but frankly, primarily, we work with Democracy, Rights, and Labor and the U.S. Agency for Global Media because this entire program is completely open source, and the goal is to release all the technologies that we've developed for people to use, and also because there is no world in which you should trust closed source DARPA code for anonymous communication. Yeah. All right, so let's talk about some really cool things that we've done, much of which has been published, but not all. I'm going to skip Raven. STR is pretty wild. We are embedding messages in the generation of images. It's called semantic steganography because don't think of it as steg. It's kind of misleading. Also, semantic is kind of misleading. It's really an encoding. Basically, the underlying message drives the encoding of the image, right? So the structure of the face is the message. You can do that with GANs. The challenge is that GANs aren't invertible, right? So in other words, you can encode but not decode, so we can do both. It's like 50 kilobytes per message, so it's like a crypto, like think of it as like a crypto key per message. And again, we're not gonna claim, you would be able to tell that the message is stegged, but we don't think you can show that it's, that there's a hidden message in it. And the second one, which gets real fun, is called Butkiss. I think this is in submission now. This is using, at the time, GPT-2 to build out a statistical distribution of English where we can embed crypto keys into English statements. So they were actually embedding AES crypto keys into like the Twitter, what's it called? The sci-fi like stories. So we can put like sci-fi stories that are actually crypto keys. They are reasonably readable, though they don't entirely make sense, which, you know, it's not. You can't do everything. I will say, just for fun, testing on Twitter for reasons is harder, but there was this application called Mastodon, which we've been using for years. And so the increased, anyhow, that was an opportunity. That was fun. There's only one other major social media platform that uses Mastodon, or that has used the Mastodon code base, and we weren't going to use that one, if people know what that one is. All right, next. OK. I am not going to talk about this in the interest of time, other than you should look at Usenix 2021 for something called Balboa. It achieves enormously high throughput for hidden traffic. And what it basically does is it hot swaps packets for specific services. So we don't try to pretend to be anything. We are the actual service itself, and we just swap the underlying packet space. And if you do it fast enough, and just to be really clear, because we're talking TCP, you have to do it very, very fast. You can hide completely. And so we've thrown like supervised machine learning at this thing, and we still can't find it. Also, fun fact, throwing machine learning at encrypted traffic flows will almost always fingerprint what the traffic is. So just because it's encrypted doesn't mean you're actually hiding what you're doing. And I'm hoping most people here know what that is true. OK, next. We're doing a bunch of work helping Tor with Obfus, which is look like nothing. Hard to talk too much. I mean, there's just not much more to say about that. They're doing really great work, and we like what they're doing. The thing I'm really excited about is there's a technology called domain fronting, which is basically you bounce traffic that you need to send off of common places that are available on the internet. So think cloud providers. And then you bounce it off the cloud provider, and then you're able to get to where you actually want to go, and then the bad guys can't tell where you're going. That works great when the cloud providers and the CDNs are OK with that. It's a complicated tale as to how that can be not so great these days. Read the news, look up domain fronting and other companies. Doesn't matter. 2 slides ago, I showed you a bunch of ways in which we can do very low rate comms. And so the question is, could I use my really, really secure, so these guys, can I use the really, really secure these guys and then build a framework for this that actually does what amounts to domain fronting based handshakes for, say, Tor bridges, which is actually what we're doing under something called Moat. And so I don't have to use domain fronting anymore. Domain fronting is a great tool, by the way, but it's just, in case it goes away, the internet freedom community really should have other tools. OK? All right, on the MPC-based stuff, again, this is super new and hasn't seen the light of day. There's a tech called Kestrel. It's MPC-based messaging. It uses committees to achieve various, sending of things from Alice to Bob. The point here to recognize that's like really different is that it's not just end-to-end encrypted, but the addressee. So if Alice is sending something to Bob, the value Bob is encrypted, right? And then the servers are using MPC to actually pass the messages. And you get metadata security for free because of that, right? Because the underlying servers don't even know what they're doing. This thing can live anywhere, IoT, Raspberry Pis. We've put it in multiple cloud providers. You can pull boxes out. You can put boxes in like as they're working. It takes, at the scale of like hundreds of, like we can support like thousands of users and hundreds of thousands of servers. It takes about a minute to send from, anyhow, it's not like the most efficient thing in the world, but it's pretty darn cool, and I'm really looking forward to this thing being open sourced, but it may be a while, but just FYI. Okay, so let's talk about some lessons learned. At the time, what can go wrong when you're putting really, really distributed and hardcore MPC protocols over really crappy links, like obfuscated links? And it turns out a lot can go wrong. Like everything can go wrong. They talk different languages. The things that the MPC people want in terms of message passing is just a completely different freaking language from like, and you might have thought that, oh, well, because we start with like pluggable transports from Tor, like it's kind of similar. Not similar at all. Tor was designed for these kind of longer term channels, and a lot of what we're doing is shorter term, and we need to spin up a lot more of them, and it was just like a nightmare. We focused a lot on the underlying statistical distributions of the underlying traffic, but that was only half the story. The other story was the user models. So to put another way, if I'm hiding a hidden message in a tweet, but I'm tweeting at rates that are uncommon for Twitter users, I'm still going to get caught, right? And there's that paper called Raven that I mentioned a couple slides ago that really gets into this. But anyhow, it is a thing that we've been trying to contend with. If you want to do some like more, because crypto, we have a really cool paper also in IEEE Security and Privacy from last year on actually building out more like hardcore models. Testing. When you're talking about thousands of clients and tens of thousands to like tens of thousands of like server nodes for the distributed, it's extremely difficult to test that realistically. We thought we could do it in AWS. We absolutely could not. Most of what we're doing right now is real world testing for some definition of real world. And then race really works if you kind of ignore the user model issue, and if you just say, oh, well, there's no way that you would look at like someone tweeting at rates that would never, ever, ever, ever happen, then actually it turns out that we can actually do this MPC thing on hidden channels, and it still takes only a couple minutes for end-to-end messages. Which, just to be candid, like even this I find shocking. Like whether it'll actually work in the real world, like there's a lot more work to be done, but it does actually work. And finally, in the last minute that I have, I do want to give a shout out to some of the work that we've done in AI for internet freedom. In particular, there's an amazing number of companies, or entities rather, that are looking at measuring censorship. And they're kicking out like a crap ton of data in order to do that. And what we really need is AI, which is not a statement I love saying, but what we really need is AI to actually try to help interpret what that data means. Okay, and so here are 4 different teams that we've funded and the stuff that they've done. Censored Planet, which is done by Roya and Safi out of Michigan, her team, it's helped them do massively faster and more fine-grained understanding of what's actually going on. They also published a great paper on actually looking at the middle boxes that the Russian censorship regime is deploying at their ISPs, which I highly recommend you read. Siphon, which is an internet freedom VPN, went from looking at a couple of anomalous events a month to being able to look at anomalous events across their VPN at line speed and kicking up error messages within their internal Slack, like within minutes, which is orders of magnitude more efficient, right? It's night and day. We actually built a model that was building a predictive technique for what social media posts are likely to be censored in China, and we're working with United States organizations to try to help enable free communication there. We are not going to open source that tool because we actually realized that if we released it, other people could use it as a function of the way to figure out how to censor, basically, because it literally will take like an article and it'll like highlight in red what's going to get censored. And we're like, well, that's not great to release. But DARPA didn't make that decision. We actually talked to the US Agency for Global Media and asked their opinion, and they didn't want it released, so then we didn't release it. So sorry, but it was a little hot. And then finally, I want to footstomp. Amir has this great paper on how the Great Firewall is detecting and blocking fully encrypted traffic. And we're done. Yeah. And I got to the end. Thank you very much.
Yeah, thank you very much. We are pretty over time now, so let's take questions offline and enjoy the lunch.